All right, so this screencast is going to take you through how to tell the difference between an empirical formula and a molecular formula. You're not only going to learn how to tell the difference between them, you're also going to learn how to calculate them. There are some steps involved, and if you follow the steps, it makes it really easy each and every time. So first of all, what is the difference? Well, an empirical formula is the simplest formula. It's the smallest whole number ratio of the atoms in a compound. Another way to think of it, it's the most reduced form. It's not always the true formula though. You can take a true formula and reduce it down, and I'll show you that in an example. But in order to calculate a molecular formula for a molecular compound, you have to know the empirical formula going into it. So the molecular formula represents the total number of atoms present in that compound. So this would be the true formula, and this would just be the simplest, most reduced formula that you could use to calculate this. Remember, these are molecular formulas that we're going to be working with, so you can't balance charges to figure them out. You have to experimentally figure them out. An example would be looking at something here where you have the molecular formula of C2H2. But the empirical formula would be CH, so it would be the most reduced form. But you could have many molecular formulas that reduce down to this. But remember, each compound is different, so the molecular formula is the true formula, whereas the empirical formula is just kind of your stepping stone to get there. And here's an example of this. So if I'm looking at like benzene, which is C6H6, you'll notice that all three of these, the CH, the C2H2, C6H6, all three of them have the same percentage of carbon and the same percentage of hydrogen. That's because they're all in the same ratio. They're all in a 1-to-1 ratio. If I were to change the ratio, then I would obviously change the percentages. But what's different about them, what makes them different compounds, is they do have different molar masses. So the empirical formula has the molar mass of 13.02. C2H2 has a molar mass essentially doubling that, but C6H6 has the molar mass of 78.12. So what makes them different compounds is they do have different molar masses. So here's some molecular formulas, and I want you to give me the empirical formulas for them. So there's glucose, C6H12O6. When you reduce that down, I can take a 6 out of everything, and I end up, when I take a 6 out, with 1 carbon, 2 hydrogens, and 1 oxygen. So these ones going down, I want you to try them, although the answers are going to follow. So C2H4O2, notice it has the exact same empirical formula, but they are not the exact same type of sugar. They're not the exact same molecular formula. CO2 and then C10H15. Notice in this case, the empirical formula and the molecular formula are the same. I can't reduce this down anymore. I already have 1 atom, because remember, we can't have partials or halves. So the empirical formula is nothing more than the reduced molecular formula. It's a combination of the elements in their lowest ratio. You can think of it like reducing fractions. What number can you take out of each to reduce it down? And then the molecular formula is the true formula, or the actual formula. The actual ratio of atoms. No two compounds can have the same molecular formula. So, like I said, in order to figure out what the molecular formula is, you have to first figure out what the empirical formula is. And I'm going to have you guys do it first just with calculations where I'm going to give you the data. I'm going to give you percentages. When we do this in the lab, you're going to find your own percentages. So you're going to be given a compound that you don't know what it is, and you are going to have to calculate the empirical formula for it. But here, when we're solving the problems, I'm going to go ahead and give you that data so you don't have to experimentally find it, then calculate it. I just want you to see where we're going with this. So here's the rules. Here's the steps. All atoms have to combine in whole number ratios. Remember, we're never going to have fractions. This actually becomes very important when we're doing our calculations, because if you end up with fractions, you get to double it. You need to know the specific atomic masses of each element. Well, the nice thing is, where can you find the atomic mass for every element? On the periodic table. And we're going to know the elements involved by experimentally, figuring out what elements are involved. That's generally going to be given to you or going to be known But you have to experimentally, like in the real world, you would have to figure out what elements are involved. You are just trying to figure out their subscripts for their formula, what ratio they're in. So what we want to do is find X and Y. So basic steps to calculating. Number one, we're going to assume that we have 100 grams. So if a starting quantity isn't given, we're going to do 100 grams. That makes it really nice because you're going to be determining percentages, and percentages are based out of 100. So we can just take the percentages and turn them right into grams. What is important here is that we need all the masses to be in grams. If they're not, we have to convert them here. This is where conversions might come into play at. If it's in kilograms, convert it to grams. If it gives you in moles, convert it to grams. A lot of college chemistry labs are notorious for giving you things in the wrong units for what you need to start with, so you have to do conversions first thing into the units that you do need. So step number 2, convert the grams of each element into moles of each element, and we're going to use the molar mass. So we are going to start with, like, let's say I had 50 grams of element A and 50 grams of element B. I would use the periodic table to convert those to moles. So remember how to do conversions. This is actually why you learned how to do conversions, because we have to get things to moles. Step number 3. This is probably the trickiest one to explain. You are going to convert each of these to moles. So you might have, moles of A and moles of B. What you're then going to do is divide each value that you get in step 2 by the one that's the smallest. So if you get a value of 1.2 and a value of 0.9, 0.9 is the smallest. So you're going to divide everything by that value. After you divide everything by the smallest one, if you end up with all whole numbers, no decimals, those are your subscripts. So if you end up, with 1.001, that's a whole number of 1. If you have 1.99999, that's 2. It's close enough to 2, you're okay. If you end up with 1.5 or 1.49 or 1.75 or 2.5, those are not whole numbers. You can't round those up. They're not close enough to round. So if they're whole numbers, those are your subscripts and you're good to go. If not, you have to go to step 4. And step 4 is where you're then going to multiply those values by the smallest number that will get them to a whole number. So 1.5 you would times by 2 to get it to 3. And if you multiply that one, you have to multiply all the others. So let's go through an example really quick. We're going to calculate the empirical formula of a compound that I have calculated in the lab that contains 11.19% hydrogen and 88.79% oxygen. So my first step is I have to express everything in grams. Remember, we're going to assume a starting quantity of 100 grams, so that makes this nice. All I do is just change the percentages to grams. So I have 11.19 grams of hydrogen and 88.79 grams of oxygen. Step number 2, I'm going to convert these to moles. So 11.19 grams of hydrogen divided by 1.008 grams of hydrogen gives me 11.10 moles of hydrogen. And then 88.79 grams of oxygen divided by 16, because that's the molar mass, equals 5.549. So I have now just converted these 2 units to moles. I used dimensional analysis, used my T boxes. So my step number 3, I'm going to divide by the smallest value. In this case, my smallest value is the oxygen value of 5.59. So if I take 11.10 divided by 5.549, I get exactly 2 for the hydrogen. And obviously 5.549 divided by 5.549 is 1. So that's going to be the whole number of 1 for my oxygen. These are now going to be my subscripts because I have a whole number. These are exact whole numbers, so no step 4 is needed. My final answer is H2O. Example number 2. I'm going to do the same thing, but this one has 3 elements with it. So I want you guys to try this one. The steps are outlined there for you. Convert them all to grams, then convert to moles. I have outlined all the steps. Divide by the smallest. And you'll notice that I get whole numbers of 213. And I'm going to keep it in that order. And that's my formula. K2CO3. My next example, I go ahead and start you off with grams. So a starting quantity is given, so these are the gram amounts that I'm going to use. Step was already done. Convert to moles. This is like experimental data. This is the type of stuff you're going to get in your lab when we do empirical formulas. The lab that we're going to do. So I convert each to moles. So I convert the grams of iron to moles of iron. And I convert the grams of sulfur to moles of sulfur. And I'm going to pick which one is the smallest number. In this case, the iron is the smallest number. So I'm going to divide everything by the smallest number. And you'll notice I get 1 of iron, but I get 1.5 of sulfur. So I'm going to have to go on to a step 4. In this case, I can't have 1.5 atoms. So I can't put that as my subscript. So I'm going to have to multiply 1.5 by 2 to get it to 3. So now I would have 3 sulfurs. But if I multiply that by 2, I also have to multiply this by 2. So since I multiplied one value, I have to multiply the others. So if I take 1 times 2, I get 2 irons. 1.5 times 2, I get 3 sulfurs. And now that becomes my empirical formula, Fe2S3. This is how you would decide which type of iron you have. So you'll notice that this is an ionic compound, but iron is one of those that forms multiple oxidation states. So we don't know if it's iron 2 or if it's iron 3. You have to experimentally find that. And that would be how you would figure that out. Here's some multiplications you might use. 1.5 times 2 is 3. 1.3 times 3 equals 4. 1.6 times 3 is 5. So those might be some multiplications that you might have to use with some numbers you get. So a molecular formula, which is the actual formula, that's our final step to this. In order to calculate the molecular formula, the first thing you need is an empirical formula. So it might give it to you. It might have already been determined and give to you in the problem, or you might have to experimentally or calculate what the actual empirical formula is, because you need the molar mass of the empirical formula. So this is just going to be one more step added on. You will then divide the molecular mass by the empirical mass. The molecular mass should always be bigger, or at least the same as the empirical mass. You're never going to get anything less than 1. These are all going to be whole numbers. So you're going to divide the molecular mass by the empirical mass, and then you're going to multiply that answer by each subscript. So when I multiply the molecular mass divided by the empirical mass, if I get 2, then I'm going to multiply all the subscripts by 2, and that'll tell me what the molecular formula is. And remember, this is going to be experimentally found. So it's going to be given to you because it will have been found through experimentation. And then this you can also find through experimentation, or if the data is given to you. So here's an example of one. And in this one, I'm really nice. I give you the empirical formula is CH4N. But I want to know what's the molecular formula if its molar mass is 60 grams per mole. So what I've done is I have told you the molecular mass for the molecular formula, or the molar mass for the molecular formula. That's the number that's going to go on top. I am now telling you the empirical formula, so you have to calculate the molar mass for that, and that would be the number that goes on the bottom. If I take, let's say it's about 30, 60 divided by 30 would be 2. So my subscripts are all going to be multiplied by 2. And so my molecular formula would then be C2H8N2. If I ended up with 60 divided by 20 and ended up with 3, then I would have C3H12N3. So I want you to try to work through these examples. So there's 3 examples, example 1, example 2, and example 3. And you'll notice in all of them I've given you the empirical formula, just so you don't have to do that extra work. But in reality, in the real world, you're not going to be given the empirical formula. You have to experimentally calculate it. So we will go through the examples of calculating empirical formulas as well as calculating molecular formulas in class. So here's a few other example problems for you. Which of the following is an empirical formula? Try to identify that. And if this is the molecular formula for vitamin C, what is the empirical formula?